Here we're going to look at the dispersion equation. We begin by defining the wave number k as 2 pi over L and the wave angular frequency omega as 2 pi over T. Now the wave celerity C is defined as the wave length L over the wave period T. This is something that most of us may be familiar. It's similar to velocity, and the unit is also the same, is meter per second. But wave celerity is not velocity. We will make a distinction between these two later on. So meanwhile, since C equals L over T, we can substitute L from wave number over here, and we can substitute T from the wave angular frequency here, so that C is also equals to omega over K. Now meanwhile, we know that the wave celerity C is equals to this expression, whereby it depends on the water depth D. So what we can do next is that if we write C as omega over K and C as this expression from here, then we may be able to simplify this so that we get the dispersion equation, which looks like this. So what does this dispersion equation tells us? We see that the wave angular frequency is on the left hand side, the wave number is on the right hand side, both inside and outside the tangent hyperbolic function, and we have the water depth D over here. So essentially, from this dispersion equation, we know that in linear wave theory, K and omega are related for a given water depth D. And we also can see that the wave amplitude or wave height is not part of the equation, meaning to say that the wave amplitude is a small and a free parameter. If we expand the expression that we get from the previous slide, C equals L over T, and we also get this expression C equals to square root of G L over 2 pi K, where 2 pi over L is basically the K, the tangent hyperbolic, 2 pi D over L, whereby 2 pi over L again is basically the K. So you can see that we already come across this equation in the previous slide. So what we're going to do here right now is that we're going to focus only on this part, and we are going to simplify it so that will lead us to this expression over here, whereby the wavelength is given by this expression on the right hand side. We notice that the wavelength depends on the water depth and also the wave period. In order to solve this equation for a given location with a certain water depth and for a given wave period, we will be able to solve the L only by trial and error, and you can either do it manually or use a calculator. Now this is the equation that we get just now. L equals to gt squared over 2 pi times tangent hyperbolic of 2 pi d over L. Now what we're going to do next is that we are going to look at deep water, transitional water, and shallow water, which is distinguished based on the relative depth d over L. That means what is the water depth compared to the wavelength. If the water depth over the wavelength is more than half, then it's considered as deep water. If d over L is less than 1 over 25, in some cases is taken as 1 over 20, then it is considered as shallow water, whereas any other value in between is known as the transitional water. Now this is a very important concept. Okay, if the water depth is more than half of the wavelength, then is considered as deep. Why is that so? Because if the water depth is large enough, then the wave orbital motion will not be able to reach the seabed. On the other hand, if the water depth is small compared to the wavelength, then the orbital motion will occur even at the seabed. So this is how we distinguish between deep water and shallow water. In deep water, there's no orbital motion at the seabed. In shallow water, there will be orbital motion at the seabed. In other words, whether the water is deep or shallow is not dependent on the actual water depth itself. It's dependent on the wave compared to the water depth. So for example, if you have a 10-meter water depth and you have a 20-meter wavelength, 10 divided by 20 is half. So even though you have 10-meter water depth, the water is considered as deep if you have a wavelength of 20 meter. But for the same 10-meter depth, if you have a wavelength of 50 meter, then you may be getting a transitional or shallow water depth. So the absolute depth is not important. It is the relative depth which defines whether the wave is a deep water wave, a transitional water wave, or a shallow water wave. Now, when DOL changes, 2 pi DOL also changes. Basically, we are just multiplying 2 pi to DOL. If DOL is more than 1/2, 2 pi DOL will be more than pi. You can work this out. Whereas for shallow water, it will be 2 pi DOL will be less than 1/4, and for transitional is in between. Now, the changes in 2 pi DOL will affect the value of tangent hyperbolic 2 pi DOL, which is part of the expression. So what happens is that for deep water, if DOL is more than half, when 2 pi DOL is more than pi, then tangent hyperbolic of 2 pi DOL will be equals to 1, approximately equals to 1. For shallow water, if DOL is less than 1/25, 2 pi DOL will be less than 1/4, such that tangent hyperbolic 2 pi DOL will be approximately the same as 2 pi DOL. Which means that for deep water, we can make a simplification for the expression tangent hyperbolic 2 pi DOL. For shallow water, we can also make a simplification for this expression tangent hyperbolic 2 pi DOL, but we won't be able to do the same for transitional water. So let's look at this expression again. This is the general expression. For deep water, when tangent hyperbolic 2 pi DOL is approximately equals to 1, then this expression is equals to 1, so then it is not important anymore. So that the wavelength at deep water, denoted as L0, is now equals to GT squared over 2 pi only. Now what this tells us is that in deep water, the wavelength depends only on the wave period and is not dependent on the water depth. That's because in deep water, the wave doesn't even interact with the seabed, so the water depth is not important, and so the wavelength depends only on the wave period. Now if we know the deep water wavelength L0 is equals to GT squared over 2 pi, then the deep water wave celerity is L0 over T. So if we substitute L0 from here, we get the expression for C0 as well, which can also be written in this form, and you can work it out yourself. As mentioned just now, for shallow water, DOL is less than this value, so that tangent hyperbolic of 2 pi DOL is now approximately equals to 2 pi DOL. So going back to the original equation, For shallow water wave, L equals to gt squared over 2 pi, and this part can now be simplified as only 2 pi d over L from here. So if we simplify this expression, we are going to end up getting this expression, whereby C equals to square root of GD. Now you will need to work this out to see why L is missing and you only get C. Okay, because of the L squared and the T squared over here, we end up getting C squared and eventually C only from this expression. But since you know what is C, you can work out L again, because L is equal to C times T. So basically the wavelength L in shallow water will be given by this expression. Now, what do we observe from this simplification? For shallow water wave, the wave celerity is dependent on the water depth only and is not dependent on the wave period. So what it means here is that in shallow water, where the wave interacts with the sea bottom, the wave celerity depends only on the water depth and is no longer dependent on wave period. This figure shows us the propagation of the same wave from deep water region to transitional water region and eventually to shallow water region. When we say it is the same wave, it means that this wave has the same wave period. It is a monochromatic wave with a single frequency, a single wave period. Now, in the deep water region, the water depth is larger than the wavelength, so that the orbital motion does not reach the seabed. However, when it comes to transitional water, when the water depth reduces, then the D over L also reduces. And you notice that here the orbital motion begins to interact with the seabed. In the deep water regions, since the water depth is too large, it's not important to the wave. So the wave celerity or wave length depends only on the wave period. But when eventually the same wave arrives at the shallow water region, where the orbital motion interacts with the seabed, then the wave period is no longer important and only the water depth governs the wave celerity. Now, this transition from deep water to shallow water is a transition of water depth such that the wave energy becomes increasingly concentrated. And as the wave energy becomes increasingly concentrated in a limited water column and started to interact with the seabed, that is where the energy dissipation begins to happen. Of course, if the seabed is erodible, then the concentrated wave energy will erode the seabed. And let's say if we disregard that, another form of wave energy dissipation is the process whereby wave breaking takes place. What happens is that as the same wave propagates into the shallow water region, the circular orbital motion becomes increasingly distorted. When it becomes increasingly distorted, the sinusoidal profile of the wave also becomes increasingly distorted, so that the wave crest becomes sharper and sharper, so that the wave height increases because of the concentration of wave energy. And because the wave height increases, and at the same time the wavelength actually decreases, causing the wave steepness to increase, and at the end wave breaker is being formed in the surf zone, whereby the wave crest curve forward in order to form a breaker to dissipate the wave energy. On this slide, we look at the water particle displacement in deep water on the right, as well as in the shallow water on the left. Now we notice that in deep water, the water particle move in a circular motion, and as mentioned, the circular motion diminish at some point, so that there's no more orbital motion further deeper in the water column. However, for the same water depth, we may have a longer waves, so that the depth is relatively small compared to the wavelength, such that the orbital motion actually become distorted, and in this case it is elliptical shape. But likewise, the elliptical shape diminish as we go deeper, but it is still felt at the bottom of the seabed. So for all these cases, the orbital motion always have a equilibrium position and a displacement in the direction of wave propagation, and a displacement in the vertical direction. It has a horizontal and a vertical velocity, and we are going to look at the formulation of all this in the next slides.